All right, so we're going to find an area of a surface of revolution. So like the outside area, um, you can think of it as like a vase shape or something like that, something that can be created by rotation. So when we did volume, we figured out the rotation of, the volume of rotational solids. But more generally, we figured out the solid of any similar cross-sectional figure, right? So we're only going to be able to find surface area of solids that are created by revolution. So let me just kind of sketch out what I'm talking about. So you have your axis. Let's say you have something like this, my favorite generic curve. What I'm going to do is just rotate that around, let's say, the x-axis. So it'll end up being like that. You get this kind of hollowed out vase shape. And so we know how to find the volume of something like that. Now we're just going to figure out how to find the surface area that's on the outside, okay? And so it's basically going to be a combination of sort of what we did to find the volume of a rotational solid and what we did to find arc length, okay? So before we do that, I got to get some basic geometry facts down. Not even necessarily so basic, but what I'm just talking about is a geometry formula that we may not be super familiar with. All right. Okay. So we know that if we were to cut vertically down a right circular cylinder and lay it flat, the figure we get is basically a rectangle, and that rectangle would have a width that's just the circumference of the base, so 2 pi r, and would have a height that's just the height of the cylinder, so h. So then we can say that the volume of any specific cylinder is just 2 pi r. I'm sorry, the surface area is just 2 pi r times h, right? Because it would be the same as just the area of that rectangle, which is base times height. Well, let's look at a little bit more of a complex figure. We're going to look at what's called a right cone, a right circular cone. And it has a base that's a circle with radius r and a slant height that's an L, okay? So if we do the same thing, same idea, we cut up the side of the slant height, and then we lay it flat like a net. This is the figure we're going to end up with, and this is what we call a sector of a circle, which is just, it's a segment of the circle. So you can think about this would contribute to a bigger circle. I can't draw all of it because it would go off of my page here a little bit, but that's the idea, right? And this bigger circle would actually have a radius that's the slant height of the cone. And what was the circumference of the base of the cone would now correspond to just an arc length on the bigger circle, right? All right, and so what we want to come up with is a formula to find the area of this sector. Okay, so this is how we're going to do that. First, we need to define something. If this sector has central angle theta, then it's true that theta equals 2 pi r over L. Now, here's what I want to show you that corresponds to. That's just arc length divided by the radius of the bigger circle. And that's true. That's just the definition of an angle in radians, okay? This is calculus, so we're dealing in radians. So one way to kind of maybe verify that intuitively for yourself is in the chat. What's the circumference of a circle? So let's ignore this circle for now, and let's just think of a circle, a regular circle with radius r. What's the circumference of that? Oh, help me out here. Do not ice me on this one. Am I muted? How do you find the circumference of a circle? Distance around a circle. What's the formula? Two by r, right? So if I follow this formula, then the angle that relates to that circumference would be 2 pi r over r, or 2 pi. And we know that that is, in fact, how many radians are in a full rotation, right? There are 2 pi radians in a full rotation. Does that make sense to everybody? So let's try another one. Theta equals arc length. The angle theta is defined by arc length over radius. Well, let's say I want to know the angle that corresponds to when I have one radius straight up and one to the side, right? That's radius r. You guys just told me that a full radius is 2 pi r. So wouldn't this just be 2 pi r over 4? That's a quarter of the circle, if that's a right angle. Then if I plugged it into this formula, the arc length is 2 pi r over 4 divided by radius, which is r. The radius cancels. This simplifies to 2 pi r over pi over 2, which is exactly what a right angle is in radians, right? So that's just the way we define a central angle in radians, is the arc length that it subtends divided by the radius of the circle, okay? So now I want to go back to our circle. So r theta would then be, in this case, defined as the arc length, which is 2 pi r, that's this, divided by the radius of the bigger circle, which is L. And that's for this circle here, right? Okay. All right, well, what I'm looking to come up with is a formula for the area of a sector of a circle. And in general, the area of a sector of a circle with radius L and angle theta is 1/2 L squared theta. All right, but we just defined theta as 2 pi r over L. So I can make a substitution of 2 pi r over L, and I can simplify that 1/2 L squared theta to pi r L. All right, so we define the lateral surface area of a cone, which corresponds to just this area, as pi r L. Okay, where L is slant height and r is radius of the base. So if you're wondering where this comes from, if that's not super intuitive, you can think of this. The area of a sector specifically would be the area of the circle, pi r, in this case, sorry, the radius is L. So we'll say pi L squared right, times the proportion of the circle that sector takes up. Well, the proportion of that circle is going to be theta, whatever your angle is, theta, over 2 pi, right? That would tell you how much of the circle my sector is taking up, right? So whatever theta is divided by a full rotation. And so then if I simplify that, my pi's canceled. I'm left with 1/2 L squared theta, right? And so that's where the area of a sector formula is coming from, 1/2 L squared theta. And then I'm just replacing theta with our definition from the previous slide. So theta gets replaced with 2 pi r over L. And then we end up with that pi r L. Okay. So we're getting to a point. Don't worry, you won't have to recreate this. You'll be allowed to use the formula. But I do want to kind of define where everything is coming from one time. So now we know how to find the lateral surface area of a cone. So lateral surface area, I mean just the top, not including the base. What I want to figure out from that, we call this thing a frustum of a cone. And all it is you take a cone and you chop the top of the cone off parallel to its base. I want to find the lateral area of the frustum, meaning I want to find the area around the outside of the surface, not including the top and the bottom. So that area. So go ahead and draw this diagram so that we're all using kind of the same variables. We're going to call the top radius, where we chopped the top off, radius 1. We'll call the bottom radius, radius 2. That's your base radius. We'll call the slant height of the frustum itself, L. And then we'll call the height of the top, the slant height of the cone that we chopped off at the top, L1. All right. All right. So from our definition of surface area of a cone, if I look at this as one big cone, so I'm just looking at the whole thing, then I can say that the surface area of that cone is pi r2, right, the base radius, times the slant height, which is L1 plus L. And then what I want to figure out is just the frustum, right? I want to find the surface area of just that piece. So what I'm going to do then is subtract off the surface area of this smaller cone that we chop off the top. So it's going to be minus pi R1 times L1. Right, and so what I'm doing is just taking off the surface area of that piece. When I subtract that off, that'll just leave me with the blue frustum surface area. All right, I'm going to simplify this a little bit. So this is the area of a frustum. It's just not a super nice formula. But here's what I can do. I can factor out a pi. I can distribute the R2 right here. And I would have R2 L1 plus R2 L minus R1 L1. And then I can group these two terms, the R2 L1 and the R1 L1. And I can go, okay, well then that's pi times and I'll go ahead and factor out an L1 from those two terms. So I'll do R2 minus R1. And I factored out an L1, so I'm going to put that right here in front. And then I have plus R2L. All right, why did I do that? It'll make sense in a moment. All right. So now I'm going to continue to kind of simplify this formula. And here's how we're going to do it. We're going to go, okay, we also have this similar triangle set up here, right? So we got these two similar triangles when we look at the cross section of our cone. So from similar triangles, I should be able to set up a proportion, right? Here's the proportion I'm going to set up. L1 over R1. Okay. So that is small hypotenuse over small base is going to equal big hypotenuse, which is going to be L1 plus L, over big base, which is going to be R2.
Mr. Toller, I don't know if you're writing stuff, but it's Mr. Toller. The screen is oh, it fixed.
It updated?
Yeah.
I'm sorry. It's not. It's doing okay for me, but this Zoom update has sometimes messed things up. Let me just make sure. I'm going to do an unshare and then reshare. Go Gertz. All right, can everybody see that okay? No crazy blurs? Oh no. I think my internet's a little laggy because I have both children home on Tuesday, Thursday, and everybody's sharing the Wi-Fi. And because you guys look... Oh. Hold on. All right, so I can just multiply. I can kind of cross multiply here, right? And I'll end up with R1 times L1 plus L equals R2 L1. Distribute that R1 on the left. So I'll have R1 L1 plus R1 L equals R2 L1. All right, this guy I'm going to subtract over. to this side. So that's going to leave me with R1L equals R2L1 minus R1L1. Factor out an L1 on the right-hand side. R1L equals R2 minus R1 times L1. That's what I really wanted to get to. Because if we look back up at my blue equation, the last line of my blue equation, I have that R2 minus R1 times the quantity times L1 here, right? So now I know I can replace that with R1L. So I'm left with pi times R1L plus R2L. All right, so I can factor out an L here. Let's see, oops. So I'm going to go to the left-hand side. So I can factor out an L. I get pi times R1 plus R2 times L. And the other thing I'm going to do, this is kind of weird, I'm going to define R as 1/2 R1 plus R2. So you can think of that as the average radius of the frustum, right? So that's just the average of the radii, the smallest radii, which is at the top, averaged with the biggest radii, which is at the base. And I can replace R1 plus R2 with just 2 times that. I'm going to go replace it with 2 times 1/2 R1 plus R2 L. So you can see that's the same because, right, the 2 and the 1/2 would cancel technically. All right, but now that lets me rewrite this in a much nicer format, 2 pi R L. And so this is meant to be kind of a much more understandable and intuitive definition of surface area for a frustum, right? Because basically what it is, you take the average circumference of the frustum and you multiply it by the slant height. Whoops. And that leaves you with the surface area around the frustum. So it's just average circumference between the bases multiplied up the slant height. All right, let me pause here. So we've done it. Is similar to how we always start integrals. All right, so we're going to take this figure. I'm going to kind of draw on it. And so this is our generic on the left, just our generic sort of vase that we're trying to find the lateral surface area of, right? So just the surface area around the sides. We're not worried about the bottom base or the top base. So to do that, the first thing we'll do is subdivide it into some finite number of intervals, right? And then we'll look at the corresponding y values to each one of those intervals. So let's say I'm just going to generically call this x, this is xi, so that makes this xi minus 1, okay? And so I want to look at the y values there. And this is a smooth curve, but I can approximate that distance between those 2 points with a straight line. It's not going to be perfect because it's a curve. That curve is curving right now, right? And if you think about rotating that straight line around the x-axis, so we rotate down to here, in the chat, can you tell me what sort of figure I would get? What did I say this is called? So it's the thing we were just dealing with. It's just on its side. So just this figure here. What is that called? What?
Oh, is it the like frust?
Yeah, that's what it is. It's just a frustum, right? It's a band. It's a band of a cone. Do you guys agree with that? Because I just have a slanted line that I'm rotating around the x-axis. That's exactly what it's going to create. It's a frustum. So you can see if I continued on, I would get the end of my cone, right? And it's just on its side. Now we know how to find the surface area of a frustum, of a single frustum. So let's talk about that real quick. The surface area, the lateral surface area of a frustum is, what did we say, 2 pi r times L, where L is the slant height, right? And R is the average radius. Now in this case, so let's think about what L and R actually are in this context. Well, L is the distance between these 2 points at the top, right? And so remember what we called that. We called that magnitude of P xi minus 1 P xi. That's our generic way of saying distance between 2 points, right? Now, R is the average radius on that frustum. Well, the average radius is the radius between the bigger, the base, and the smaller base, right? So isn't it true that in this case, R would be actually, sorry, let me color coordinate here. R would be, let's just call it yi plus yi minus 1 divided by 2. Where yi minus 1 is just that y coordinate, and yi is this y coordinate, right? All right, so great. Now my surface, my area becomes of just that frustum, so I'll call it A sub I. I'm indicating we're just finding the area of the frustum over that subinterval is just 2 times pi times yi minus 1 plus yi over 2 times the distance in between those 2 points, which we said is pi minus 1 pi. Cool. Well, I tell you what, we learned in the last unit that this That's arc length. So meaning that equals the square root of 1 plus, I'm just going to call it f of xi star squared times delta x. So we came up with that formula in the last section, right? So that was just going from this kind of abstract idea of, okay, this just represents the distance between the 2 points, and creating a formula out of it. Sorry if that's a little small. All right. Well, we can think of the average radius, that piece. That's going to be some radius on that interval. That's going to be somewhere in the middle, right? So let's call that just f of xi star. Because that's just, when we average the bigger radius with the smaller radius, it's going to give us some value of the radius that's in between xi and xi minus 1. It's going to be somewhere in there. And so let's say that that equals the average radius over that interval. All right, so that simplifies our formula for us. And it becomes the area of the band, the frustum on that interval is just 2 pi times f of xi star, which is my average radius, times the square root of 1 plus f of xi star squared delta x. And that gives us that shaded area, right? The area of one band, the surface area of one band. Now, what I would want to do to find the overall area, I would want to find the area of every band on that interval, right, between A and B. So I would get a different band here. I would get another one here, and so on. And so if I could just add up the areas of all those different bands, then I could get an approximation of my overall surface area. So for that, I'm going to come up here. I'm going to say that the overall area is approximately equal to the sum over all the intervals from I equals 1 to n. So that's just for each one of these subintervals, I'm creating a frustum, and I'm going to find that area, and it's going to be 2 pi f of xi star, so my average radius on that interval, times root 1 plus f of xi star squared delta x. Awesome. So this is really important. This is how we get an overall estimate of our surface area. Well, just like with volumes and just like with regular areas under a curve, how do we get better estimates? You guys can unmute can somebody unmute yourself and tell me, how do I get better estimates overall?
Creating more like sub areas.
Sub intervals, right? Creating exactly more sub intervals, which is going to create more bands. So I would divide this up more, and it's going to give me skinnier and skinnier frustums, right? But because of that, my lines will be more accurate to my curve. I'll have a smaller sort of slant height there that's a better and better estimate of the curve. How do I get exact? How many subintervals do I need to use to get exact?
Infinite.
Infinitely many. And so all I'm going to do is let n, which is the number of subintervals, approach infinity, okay? So let me write this out. So one more time, here's our estimate formula. Because that contains a finite number of subintervals. So it's 2 pi f of x I star. And I just want to break down just so I can make sure you all understand what this is. That's circumference, right? Times the square root of 1 plus f of x I star squared delta x. That's arc length. All right, if I want my area to be exact, I just need to do this. The limit as n approaches infinity of that. Okay. Well, once we let n approach infinity, we end up with a new notation, right? So our sigma goes from sigma with n approaching infinity. This whole piece just becomes an integral. Now it's an infinite sum over some interval from a to b. My i's, my x sub i's, which were indexed, as you use more and more indices, once you use infinitely many, they basically, all the indices overlap on top of each other and you end up with a completely dense x-axis, so it just becomes the continuous variable x. So it just becomes 2 pi f of x times, same idea here, 1 plus f of x. Sorry, this is f prime, I just realized, and I had been writing it just as f. This is f prime, I apologize. 1 plus f prime of x squared, and the delta x becomes dx. And there's your arc length formula. The way, have you guys seen the X-Men movies? You know what I'm talking about? X-Men? I'm talking about the older ones where Patrick Stewart is Professor X and Rebecca Romijn is, well, you could do the newer ones where Jennifer Lawrence is, what's the name of the character that shapeshifts? Oh, help me out here. Emin, Tommy, somebody. All right, well, this analogy is not going to go over very well. It's, she's blue. Jennifer Lawrence plays her. She's all blue. And she can, like, turn into anybody. Mystique? Is that what you said? That might be right. My wife said Mystique. Yeah. So, you've let me down, Tommy. You can stick your sorries in a sack. Looking at it in a second. But the idea, right, is that you like take the circumference, which is that first piece of the formula, and then you multiply it down the arc length of the curve. So you're just taking that circumference, which is infinitely thin, and you're multiplying it along the arc length of the curve, which is sort of skinning the curve, right? It's like skinning over it, which leaves you with the surface area. So here's for the development of that circumference formula, but using it is not as difficult as developing it. It's pretty straightforward. It's just like using the other one, the arc length formula. You just have an extra thing to multiply at the beginning. So all right, so there we have our formula. Surface area is the integral from a to b of 2 pi f of x times the square root of 1 plus f prime squared dx. All right, and you can actually find surface area using any one of these formulas. So this is just, I've converted it to Leibniz notation. And we've just rewritten, instead of f of x, we've rewritten things in terms of y. So that's still f of x, right? And that's still f prime of x squared. If the integral goes from c to d, then the formula for surface area can become, you can just integrate 2 pi y times the integral 1 plus dx dy squared dy. In this case, you would leave y as the variable y. You would not, obviously, you would not replace it with the function of x. You would just leave it as y. Now, I want to make note, these are both only for rotation about the x-axis. Okay? Both of these are only for rotation about the x-axis. If we rotate around the y-axis, we need to use this formula. And I'm going to pause here because I want you to write these down, and this is the next thing I need to give an explanation of. So let's look at the top one. So the top one is where we're taking our derivative here with respect to x, and also the integral will end up being with respect to x. So if I take that, I set that equal to ds, and I square both sides of the equation. So I'm squaring everything. So this and this, right? So I end up, there's an intermediate step that's kind of not shown here. But I end up with ds squared on the left. And on the right, I end up with squaring the radical just leaves me with that, what's underneath it, which is 1 plus dy dx squared. But then that's being multiplied by the outside, which is also squared. So that's dx squared, right? All right, well, that's 1 plus, hold on, I'm sorry. 1 plus dy squared over dx squared times dx squared. When I distribute this, there, it's going to cancel the dx squared in the denominator. When I distribute it here, I'm just going to have dx squared. And thus, I'm going to be left with ds squared equals dx squared plus dy squared, right? All right. What if I do the same thing to this one down here when everything's switched? Right here, I'm taking the derivative with respect to y, and I will end up integrating with respect to y. But if I square both sides, all right, on the left-hand side, I end up with ds squared. On the right-hand side, I end up with what was under the square root, 1 plus dx dy squared. But this time it's times dy squared. All right, well, that's 1 plus dx squared over dy squared times dy squared. Right? And then now distributing the dy squared. When I distribute it to that one, it's going to cancel out the dy squared and leave me with only dx squared. When I distribute it to the one, I end up with just dy squared plus dx squared, which is again the same as this. So they're symmetric equations, meaning they actually give you the exact same thing, which is really helpful because regardless of if you're rotating around the x or y axis, you can integrate with respect to either variable, which is very, very useful for us because sometimes you may have a function that's described in terms of y. All right, let me show you this. So if I had like x equals y squared, but I want to rotate that around the x-axis, well, that's just a parabola on its side. And if I rotate that around the x-axis, it's just going to look like that kind of bullet shape, right? And let's say I want to find its surface area. Okay, well, then I have to do surface area is the integral from a to b of, if I'm rotating around the x-axis, it'll be 2 pi y, because the radii, remember, the radii are going to be these vertical distances since we're rotating around the x-axis. So 2 pi y times the arc length, which I decided to call ds. But in this case, because my function is already given in terms of y, it would be nice if I could just do everything where y is my variable. I could take the derivative with respect to y, etc., etc. Well, now I can just go, oh, okay, well, that's just 2 pi y times 1 plus dy dx squared, or sorry, dx dy squared dy. And so now I'm both taking the derivative, in this case, with respect to x, and I'm integrating, I'm taking the derivative, oh God, I wrote it backwards again, dx dy. I'm taking the derivative with respect to y, and I'm integrating with respect to y, which means I can just leave my function as is without having to solve for x. Not that it's like super hard in this case, in this scenario, okay? All right, that's a lot of abstract talk. So this took a little longer, which is fine, but we got all of the derivation out of the way. In Thursday, we'll kind of push everything back, and I'll just do, 3 or 4 concrete examples of how to use this, and then I'll give you some time to work on the problem set, all right?